It's a pleasure for me to speak to you. I think this might be the first presentation I've made that is sort of a worldwide audience. And so this is kind of interesting and fun to do. So we're going to talk about update some of those claims we tested a couple of years ago and see how the science has advanced or not advanced, as the case may be. Okay, next. Okay, so dealing with climate change claims in 2021, it can be extremely frustrating because you hear things said all over the place about it. And so we're going to look at some of those that we can test. Most of them we can't really test. The data just aren't there to answer questions about whether, a certain flock of birds landed here rather than there because of climate change or something like that. We're going to look at ones that we can test and indicate, the results indicate there really is no climate crisis. Okay, next. So the theory of greenhouse warming we're going to start off with is how do you detect a very tiny influence on a massive climate system? Next. So here's a cartoon of the climate system, and look at the atmosphere there, that bluish part. That radiates downward about 100 units of energy. One unit is about 3.4 watts, but just 100 units of energy coming down. Surface of the Earth about 105 back up, and other heat is transported as well. So if you're on the surface of the Earth looking up, you see 100 units of energy coming down, radiated from clouds, aerosols, molecules of all kinds. And the amount due to the extra carbon dioxide and greenhouse gases is less than 1 unit of that. So we've got these dozens and dozens of units, and they vary by 1, 2, 3, 5 units apiece. And we're trying to figure out what a portion of 1 unit might do to this very complicated system. Okay, next. So think of the surface temperature as a battle between things that heat it up and things that cool, like a tug of war. So you see how big those are, and notice that they are not static. They change all the time, even in the global average. They get bigger and smaller, and as they change, the temperature goes up or down. Now, what do humans do? Well, we're that little bitty guy on the end. And you can imagine that if that little guy is pushing a little bit more, could one of the others change their response? And that really boils a lot of the issues about climate change down to what it really is. What is the true response to the climate system, to that little extra pull right there you see? Okay, next. So we're going to test a claim that the current global warming is significant and that it is caused entirely by the extra greenhouse gases that human economies emit as they enhance their well-being. Is that true? You've heard it many times that all of the warming in the last 40, 50 years is due to us, to humans. And so we're going to test some of those claims. Next. So, well, to be real scientists, you have to do things with numbers and you have to measure things. So Ross McKittrick and I, a couple of years ago, looked for a variable that was very clean, that was a very clear and clean test for this hypothesis about global warming, a way to test models and what they say. Next. And so that response variable that all of the models, we should be able to see that response variable in all of the models. Next. And that response is not there when the extra greenhouse gases are not there. So, the experiment and control are always different. Okay, next. And this metric cannot be used in tuning and development of the model. And that is something that some of you might not realize, but a lot of times some of these climate modelers validate their models with a variable that they actually use to tune the model with. Surface temperature is one of those variables that models are tuned to, and then they come back and say, see, my model matches the surface temperature, it must be right. Well, that's not science. And finally, these observations could come from multiple and independent sources. In other words, you wouldn't want a climate model group to also build the data set of observations and then have them compare. There might be a little bit of conflict of interest there. So independent groups measuring, creating these measurements. Okay, next. So what we found, as I told you about a couple of years ago, was that this atmospheric layer that's about 30 to 40,000 feet in the tropics is just a big, loud, noisy, not noisy, but a loud sound that says this is what global warming is supposed to do in the models. If you look at the cross section there, the South Pole's on the left, North Pole's on the right, and the stratosphere is at the top. So this is a cross section of the vertical atmosphere. And there you see right in the tropics between 30 and 40,000 feet, this very obvious area of rapid warming. And this is a Canadian model, by the way. We were just talking about that. This should already have happened. In other words, the results I will show you from models that are trying to reproduce what's happened in the last 40 years. Okay, next. So here's the claim, and the hypothesis is that significant warming should already have occurred to change our climate. That should already be in the models and in the real world. So let's go to test that now. Next slide. These are brand new results. You have not seen these before. These are 39 of the CMIP6 models. Now, if you look carefully, you might find your favorite model there on the bottom. You can see a couple there on the bottom left, about the 6th and 7th over. Those are two Canadian models right there. There are a number of Chinese models now. So the average of all of those models, and they're all pretty consistent here, is about 0.4 of a degree per decade should have happened by this time. In other words, that is a test that we can now go. By the way, those two Canadian models are way up there. In fact, I think we did a little study, and if the model came from an English-speaking world, it was always pretty high. I don't know why that is. There you see the UK model and the Access model from Australia and so on. So what did the real world do? Now, this is a very simple hypothesis test, right? The real world came out with 0.17 of a degree per decade. Observation, experiment versus the observation. And you see in typical scientific world, we would say, well, our hypothesis has failed. In fact, all 39 of them have failed. Even the Russian models are going warmer now than they used to. So we have a pretty clear picture here that models are not doing well. And don't let someone say, oh, but that's the air up there at 30, 40,000 feet. That doesn't matter. We live at the surface. Remember, a climate model is a system of physical attributes. Physics operates. And if you don't get a major part of the world of the system correct, you cannot say my system is modeled correctly. And this is a very important part of the atmosphere because this tells you how you release heat to outer space. Okay, next. So here is the last picture I showed you. These were the CMIP5 models, and you can see that we did the test on them. They were the average was significantly different. Ross McKittrick and I published a paper just this year, 2020, about this very metric with the new CMIP6 models, and sure enough, they are significantly different, highly significantly different than what the observations show. Now, kind of fix your eyes on that chart, and I'm going to go to the CMIP6 model. So fix your eyes for a moment on that chart, and now let's go right to CMIP6. Now, I think if you saw something change, it was the variability of these models. Look how much they bounce up and down relative to the last picture. So the variance is quite high in these new models. In fact, on average, the variance is 4 times that of the real world. Now, if you look at the green arrow and the green observations, you see that the real world doesn't stray too far from the long-term trend. That's a system that has lots of negative feedbacks, that once it gets away from the mean state, it comes back. If you look at the models, they stray very far, which indicate they don't have the negative feedbacks in the proper proportion, that the negative feedbacks don't kick in until they're way too hot. Now, that has a very important point when you talk about adding a gradual forcing of extra greenhouse gases. Because that means as you add an extra forcing, you are not being able to provide a negative feedback against that forcing. And you see that the trends then go 2.5 times too fast. In fact, there in the blue box, I notice in the second line, I say when you go to the next 30 years, the trend gets even higher than it has been for the last 40 years. But we don't see that in the observations. In fact, this coming year, the satellite data we've been looking at, because of the La Nina, the temperature has fallen back a good bit. All right, next. So one of the things, and I showed this last time, that we found is that regarding those feedback processes, when we see that the atmospheric column warms up by a degree, models send out only 1.4 watts. The real Earth sends out 2.6 watts. That's a very strong negative feedback. In other words, it's real hard for the global atmosphere, the real atmosphere, to get much hotter than it is because it sheds so much heat. Whereas in the models, they trap heat. They trap more heat than the real world does. And so that's how their temperature can continue to rise over time. So the flow of energy is misrepresented in these models. I just showed you that the actual, the models don't even match the past, and they really don't agree with each other in the future. But now you see that the energy flow, the basic physics of it, are not maintained in the largest scale, the global scale. Okay, next. Now this is kind of interesting and new. The red line is the observational absolute temperature of this layer. It's about 231 kelvins. And you can see it goes along. It doesn't bounce up very much at all around, and it's fairly level. There's not much of a trend there. But you can see some of the models have large variances, as we mentioned before. But look at the spread. Now remember, this is the absolute temperature. And there are physics in the models that require the absolute temperature to be correct. For example, if a black body is radiating at sigma t to the fourth, t to the fourth has to be right. So if you have a layer that's emitting, that's opaque, and sometimes this layer up there does become almost opaque so that it radiates nearly as a black body, certain kind of clouds or water vapor get up there. That range of temperatures among the models is from 143 watts to 168 watts on average. That's a huge range and can stray very far from the fundamental physical number of 159 watts for that black body. So this tells you, again, another energy story here is that the energy exchanges and representations in the models just aren't matching up because the temperatures aren't matching up with their absolute values. Okay, next. So if we go 120-year experiment here in 1980, we start with our observations. You see they're just muddling along a little bit. But we look at two other scenarios for the climate models, and you can say that we are 1/3 of the way in this period to 2100, 1/3 of the way. It's only 80 years away, 79 years away. We already have 1/3 in the can, and you can see the models are off. They're just not replicating what we've already done. You know, in any other science, if you have a period of time you're testing, and you go through the first period and you're already off by a factor of 2.5 on the rate of warming, you say, I better stop, and I'm going to go back and see if I can fix something. That isn't the way in climate models. They let it go because the scary story is the one that seems to get the most attention. All right, next. So this next couple of 3 slides are going to be a little bit difficult to understand, so I'll try to just explain what's going on here. I'm going to introduce equilibrium climate sensitivity, or ECS. That's just an index temperature that says how hot will the world be if you instantaneously double CO2 and let it go for another 100, 200 years or so, but instantaneously double CO2. And what's the ultimate temperature going to be? The equilibrium is reached. And so climate models have done that. You know, you can't do that in the real world. You can't just double CO2 instantaneously, but climate models you can. And they calculate a sensitivity there in the second paragraph of 1.8 to 5.6. My goodness, That is a factor of 3. What is the climate sensitivity if models have a factor of 3 variance on it? So with such a huge range, they came up with this idea called emergent constraint. It's a strange term, emergent constraint. And that's supposed to help them figure out which model might have the best ECS. Now, empirically, when we use real data, to calculate the sensitivity, it varies from 1 to 2.3. And a lot of them fall into about 1.6. And that is outside the range, as you see, of the climate models up there. The real world is outside the range of those climate models. Okay, next. So this emergent constraint, I said, is a strange term that simply means let's look at something in a climate model, a characteristic in a climate model that's sort of related to ECS. Then we go to the real world and figure out what that characteristic is. And then the models whose characteristics match, we'll say that model has the best ECS. So for example, if you have cloud cover and you have observations of cloud cover, you look at all the models, and the model with the best cloud cover that matches the real world, you say, okay, that's the model with the best ECS. Now, my explanation is very, very simple here, and I'm sure others will not appreciate what I'm trying to do, but just to be as simple as possible. It seems that going through this process of finding some kind of tangential metric that might validate your model is just not very smart to me. So Ross McKittrick and I, this past year, used an obvious metric. Well, how about an emergent constraint like the global temperature trend? Why not use something very obvious that is related to ECS, to the equilibrium climate sensitivity, like the global atmospheric temperature trend? Okay, next. So our result shows this in the squares at the top. Oh, there are 2 layers to the atmosphere we're looking at here. Satellites produce, one's mid-troposphere, one's lower troposphere. So the mid-troposphere, I believe, is the open circles and squares, and the lower troposphere is the solid circles and squares. Anyway, so the models kind of group themselves, and there's one kind of big group that's up there, very high ECS, that's on the vertical axis, and the emergent constraint is on the horizontal axis. So you can see the emergent constraint is the trend of their troposphere, either the lower or middle, depending on solid or open. Then there's a group of models that have a less ECS, that's the blue in there, and so we put crosses at the mean of those 2 groups and then extrapolated down to 0, 0 from the lower group. Because if you have no climate sensitivity, you would have no trend, right? And so the real trends are those 2 arrows there, those vertical arrows for the mid-troposphere and the lower troposphere. So that is the emergent constraint in the real world. And when you use the model-based relationship of ECS to our characteristic, the trend, you come out with you come out with a 1.4 to 1.7 value. Okay, so that's a little complicated, and you might have to go back to read the paper to grasp this on such a short notice. But the idea is we took a characteristic, the global atmospheric temperature trend, and related that to ECS in the models, and then used that relationship to say, well, here's the real global atmospheric trend. What's its ECS? And it comes out to low value. Okay, next. So what we've come to is that, the models represent our level of understanding, or more importantly, our level of misunderstanding about the system and about how the impacts of greenhouse gases affect the climate. So as hypotheses, do they succeed in describing the attributes of the physical climate system so well we can use them for policy to take money out of your pocketbook? Well, I've shown you models fail to reproduce the past, pretty significantly, by the way. Models fail to reproduce the accurate energy flows, and this is the guts of how a climate system works. It's how the energy flows between places. And finally, models disagree with each other about the future. So which model are you going to pick? If you pick the Canadian one, we're all going to fry. So the weather, now, so that's the model section. Now let's go on to the weather that people really care about. We're going to show it's not becoming more extreme or dangerous. And people are getting smarter by the day in dealing with weather problems. Okay, next. So you've heard the stories in the media, of course, that all extreme weather is getting worse and it's your fault. And remember, media want to get eyeballs, your eyeballs on their webpage or on their television or so on. So it's got to have something dramatic on it. Whether it's true or not, that's a different question. But it's got to be a dramatic visual. And what gives you more dramatic visuals than tornadoes and hurricanes and droughts and floods and fires? You know, that's great stuff for the video. Okay, next, let's check this out. Here's some headlines about the Atlantic hurricane season of 2020. It's devastating, breaks all-time record. Gulf Coast, and my state is on the Gulf Coast, is battered. Well, we didn't have much damage here at all on the Gulf Coast. Notice in The Guardian, they're easy to pick on, by the way, for finding false statements. The Guardian here says, dozens of people have died this year as Theta becomes 29th major storm. Now, think about COVID. We're talking about millions of people dying from this disease, but what does The Guardian do? Dozens of people have died. It's a pretty small number. Okay, next, let's look at the numbers. On the left, you see the Atlantic hurricane season. 2020 is in the blue, and it is above the red average. Now, 1933, you can see the number was much higher. This is the accumulated cyclone energy. So this is the best metric because it tells you not only how long the hurricane lived, how fast it was, how devastating it was. So it adds up all that energy. It's the best way to describe a hurricane season. In 1933, there was about 50% more ACE than in 2020. So 2020 was not the worst year for hurricane energy. Now go to the North Pacific, where the lots of hurricanes are. It's barely above half of average. Not much happening in the North Indian Ocean. So when you add the total hemisphere, Northern Hemisphere, it was below average. You can't make a story out of that, can you? 2020 year was below average in the Northern Hemisphere. And then if you go global, you'll find it was even further below average. So the hurricane season for 2020 was not anything to write home about. In fact, it was a little quieter than usual. Next. So if you look at time series, this is where 2020 ended up in global ACE. It's almost at the bottom. Interestingly, the coolest Northern Hemisphere year was 1992. That was the year with the most hurricane energy. And that tells you something about hurricanes, that it's not how hot it is, it's do you have a contrast in temperature? And it's that contrast in temperature that creates the energy that wants to solve that gradient in temperature. All right, next. Tornadoes. United States has the most documented tornadoes. And so we keep pretty good track of them. And you see that for the last 67 years, the first half of that period averaged about 56 tornadoes a year. The second half, about 34 tornadoes a year. How can you make a story out of that? Well, it's pretty tough, except to say, it looks like tornadoes are declining. Now, I'm a climatologist and have studied things for long periods of time. I would not be surprised if tornadoes turned around and went up again. It's just what they do. It's a very nonlinear, chaotic kind of system, especially in totals of these things. So I'm just saying you don't see here an increase, obviously, in tornado production. Next. Droughts and floods. So the flood is the blue. We have no real trend at all. Some months have a lot in the United States. Some months have little. And in terms of areas of the United States in drought, if there is any trend in there, it's slightly lessening. In other words, droughts are becoming less over time, at least in the United States. But the high variability is the story there. And it's not that there is any long-term change at all in droughts or floods. Next. What about high temperatures? These are the number of stations that had record high temperatures by year. And so you see here that if you want to talk about record high temperatures in the United States, you've got to go back to the 1930s. That's where the real story is. In fact, 14 of the top 15 years with the most heat records occurred before 1960. Here again is just simple evidence that indicates the extreme weather, the extreme hot days. The number we're experiencing now is the same as it was 120 years ago. Next. Global drought, we see here, there was kind of a bump there in 1983 that was related to some of the things the El Nino did that year. But overall, the trend is flat, that droughts are not increasing globally, as you can see here. Next. Oh, wildfires. If you lived in the United States this past year, especially August and September and October, it was just story after story of the terrible fires out in the West. Again, the Guardian, they're always great to attack. California's wildfire hell, how 2020 became the state's worst ever fire season. Worst ever. I wonder what that means. Does it mean like there's never been a year with more fires than 2020? That's kind of what it means. And other stories there you see about record fires, 4 million acres and so on like that. And see, like you have a video of that fire. Boy, that's just something that really catches your eyes, and that's what the news really depends on. Okay, next. Well, let's go back about 400 years and look at North America fires. And you can see here the coverage of the fires. They're quite a bit, all the way up to European settlement. And the basic idea here is that Europeans, when they built stuff and had farms, they didn't want their stuff to burn up. And so they figured out how to stop fires. Prior to this time, when a fire was started by lightning or Native Americans, it burned and burned and burned till the fall rains came. So places just got burned up like crazy. Europeans didn't like that. So they put out fires and got pretty good at it, not thinking about what they were ultimately doing other than just saving their own stuff. California became state in 1850. And you can see there that there are some pretty big wildfire extents back in 1850. Okay, next. This is me on some of my property, a little bit of property in California foothills, the places that burn up all the time. Look at what one of the most thorough studies did there in the top paragraph on the right. The blue, it says pre-European burn area was 4.5 to 12 million acres in California per year. That was the average, 4.5 to 12 million acres every year. But as I said, once Europeans got in there and they practiced fire suppression, boy, that number went way, way down. That means a lot of stuff that was dry and dead didn't burn up, and so it's laying around. And in fact, after the 2012 to 2015 drought in the Sierra of California, the forests were weakened. The bark beetles came in because the trees did not have the proper defense, being in a weakened state, and killed the trees. In fact, in places, 80% of the trees killed, but they were left standing and they dried out because California did not like you to touch any kind of Mother Nature stuff, and so you couldn't take out a dead tree. So now you've got 150 million dead trees in your forests. And like I said, in places it was 80% killed. 2020 took care of a lot of those dead trees. It doesn't take much of a fire in a very dry deadwood forest for something to get going. And so that is the situation they're living with. And even then, the total acreage in California was less than 4.5 million acres. It was not the worst ever fire season because it didn't even make it up to the average over the last 10,000 years. Next. And so I showed this cartoon before. If you want to build a house in the foothills of California, you know, you're putting it in the midst of a bunch of matchsticks ready to go. Okay, next. And then globally, everyone's getting into the act now about putting out fires. And so you see that globally, the amount of acreage burned has been falling. And the top one, year by year, satellite estimates now show these falling. And then the lower one decade by decade indicates the same thing, that the amount of forest fires and wildfires are declining because people are applying fire suppression techniques. It's probably not a good thing because some, especially in California, a lot of those biomes depend on burning every 3 years. That's the way they live and stay healthy, is if they burn every 3 years. And yet that's been not allowed, and so that has really changed the problem out there. Next. Snow, someone said about snow is never going to happen again. Well, we have satellites, and they look down and see how much snow coverage there is in the northern hemisphere. And it goes up and down year to year, but as you can see, there is no trend at all. It still snows in the northern hemisphere, okay? And to about the same amount every year. Next. We look at Arctic sea ice. Now, you got to kind of turn your brain around. If you look at the upper left picture, today is on the left and 10,000 years ago is on the right. So if you look at the past few thousand years, or from 10,000 years to 3,000 years or so, ice in the Arctic was very low. The coverage is very low, big open expanses of sea ice all the time for thousands of years. And it's only been in the last 1,500 years that you see the concentration of sea ice increasing, peaking at the Little Ice Age, which ended about 170 years ago, about 1850. So the sea ice in the Arctic reached its maximum amount or extent about 175 years ago. And has bounced back since there. Bottom right, it's another picture of the same thing. This shows low values of sea ice on top, high on the bottom, and you see that low values really dominated the period 6,000 to 8,000 years ago. So we're in a coldish period in terms of the Arctic right now. On the bottom left is the last, how many years? I believe it's the last about 40 years, last 40 years. The blue is the Arctic, northern hemisphere, and it has declined, as we've all been made aware of. The red is the sea ice around the Antarctic. And the sea ice around the Antarctic has shown an increase up to 2014. Then a series of huge storms came that busted up the ice and sent it to lower latitudes where it melted, and really dropped it to about 2017 to a low amount. And since 2017, it's been struggling back up. And if you look very, very carefully at the very last thin red line there, the monthly value, it's above average again back in Antarctica. The two basins are very different. Antarctica has no boundary as it goes to the equator, because there's just water as you go toward the equator from Antarctica, so it can grow if it wants to. Arctic sea ice is pretty much confined. I mean, it's in that Arctic basin, and it doesn't have much way to go out. It can only go down and back to normal, back down and back to normal. So it's a different kind of metric there. All right, next. When you look at sea level depends on how much ice is on land, and if it melts, it fills up the sea, and the sea goes up. So if you look at the last 5 million years on the top, for the first 2 of those million years, about 10 to 25 meters higher than it is today. Then we went into this ice age type of cycle, up and down, getting the amplitude bigger and bigger, and the lowest point lower and lower until the very last one just 20,000 years ago, where sea level went way down. If you look at the bottom left, you see that sea level in these past 24,000 years, it was 120 meters lower than what it is now. Florida was twice as big as it is now because of that continental shelf. Then the sea level rose rapidly as the ice age ice melted, especially in the North American continent, and sea level rose rapidly. And I mean rapidly, like, about 12 and a half centimeters per decade for 8,000 years. Now, what's it now, 2.5 to 3 centimeters per decade? 8,000 years, it was 4 or 5 times that. And, the world did okay as far as I can tell. Now let's look at the last 10,000 years on the bottom right. On the left, it's the sea level. You got to look very carefully, but on the left, if you look carefully, you will see that about 8,000 years ago, the sea level was 2 to 3 meters higher than it is today. And then it fell as you go to the right down to current day. And if you look very, very carefully at the very right-hand bit, you see what's happened in the last 200 years. There's been a little bit turned back up. In other words, for most of the sea ice or sea level records we have, the lowest level in the last 10,000 years or 8,000 years was reached about 1850, about 1860. And then that's when sea level started to rise again, about 1860. And that's what we'll see in the next slide. So about 1860, it started rising. If you look at the lower left, you see that that's what's happened the last 120 years. There's a pretty rapid rise there about 1920 to 1960, 1930 to 1960, similar to the rise we've seen in the last 40 years. Models have tried to reproduce the real sea level, but you can see in the green words there, it says actual model result, and you see just a very minor change in sea level, nothing like what actually happened. And then they do what they call post hoc corrections, which means, golly, my model didn't do too well. What can I jimmy in thing in the output? I'm going to take the output and play with it and see if I get a better answer. And you see it didn't quite get to what needed to be. But what it says, if we look at the column there, it tells you that 2 to 3 meters higher 7,000 years ago, 6 to 9 meters higher 130,000 years ago, 10 to 25 meters higher 3 million years ago. And that the glaciers in the past 10,000 years reached their highest extent, and therefore the sea level, the lowest level, around 1850. And then sea level started to rise at that point. And then you see the two rates of rise. The first one, we can't blame on humans. That's just Mother Nature melting ice. And the second one, though, is popular to blame on humans. About 70% of that rise is due to added water from this melting ice, and about 25% from the thermal expansion of the upper layer of the ocean. If you look at that top line, that's the last 25 years or so, and we see some satellites have gotten into this piece of information. That rises about 3 centimeters per decade. And the last, if you look at the last 5 years, there's just not much rise at all. So we're not seeing that kind of rapid accelerating sea rise that folks have been talking about. So, if you're talking about 3 centimeters a decade, that's 30 centimeters 100 years. So we're talking about this much sea level. I wonder if humanity can handle that if given 100 years. I suppose they can. In fact, what we worry about here in Alabama on the Gulf Coast is not an inch per decade. It's 20 feet in 6 hours. And that's what happens when a hurricane comes. And let me tell you, if you're ready for 20 feet of rise in 6 hours, you can handle 30 centimeters in 100 years. Okay, next. And then most important for human folks is that we see on the left the wealth we have. And we see that the wealth that is lost to these kind of weather disasters and so on has actually been declining. So we've gotten smarter about how we build things. In the upper right, we've really gotten smarter because here are the climate-related deaths from weather type events. It has plummeted. We just know better how to deal with the weather, how to forecast, how to warn people, and to build things better. And so we've seen these, both plots on the right show the amount of deaths have been declining. Now, remember what the Guardian said? Dozens of people have died from these hurricanes. When you look in the past and you see hundreds of thousands of people had died before. All right, next. So progress toward eradicating poverty is going to keep going on. And you can't eradicate poverty without energy. And energy today is primarily from carbon. And that's going to continue. Next. So I mentioned this before, but it's just such a remarkable comment is still with me that a very wealthy environmentalist, I mean very wealthy, said the Chinese lifted 400 million people out of poverty by building a coal-fired power plant every week. And next, and that was bad. He thought that was bad because it put CO2 in the air. Next. But it was viewed as good by those 400 million people, and because they're no longer living in that kind of abject poverty. In 2020, China's coal use rose to its highest level in the last 5 years. And the record cold temperatures, this really hit them this year, these record cold temperatures in parts of China in early 2021, it actually froze up some of the windmills. And so their power consumption production went way down from those renewable sources, had blackouts, had terrible situations because their energy, any energy that depended upon the renewables was just not going to come through when it really, really got cold and people really, really needed it. Okay, next. So it's just an undeniable force that no one wants to be poor, and we're going to see the rest of the world continuing on that plan of development that they don't want to be poor. And you and I aren't going to stop them. The EIA, which is now kind of a global warming aficionado, they used to be very factual and didn't have comments about things like this, but now their reports are, we've got to stop CO2 and so on. But even they look at real numbers, and so they show that the amount of CO2 will actually keep growing and won't be peaking before 2040 up there. Next. And this was an exercise I did for the U.S. Congress when they were asking, well, if we had this legislation that removed this much CO2 from the air, is that going to change the climate? If we move this much CO2, will that change the climate? I said, I'll make it simple for you. Let's just eliminate the entire United States. No people, no cars, no factory, nothing. Let's just eliminate it. And that's the impact, if you believe the climate models, that the impact is less than what we see bouncing around month to month in the global temperature anomalies. So no, even if you make the United States go away today, not just some little legislative thing about making cars go 40 miles per gallon rather than 30 miles per gallon. I mean, just take us off the face of the earth. We will not impact the climate enough to notice. Okay, next. So the 3 points that I wanted to leave you with today are the established global warming theory significantly misrepresents the impact of extra greenhouse gases. We got to get that point across. It's really hard because we're just outgunned and outmoneyed from those who want an alarming story. But we got to keep, with the scientific method, demonstrating that theories or hypotheses, I should say, can be tested, and they often fail. Second, that the weather that really affects people the most is not becoming more extreme or dangerous. And we actually know how to handle a lot of this now. And progress toward eradicating poverty based on accessible and affordable energy, which is carbon today, is continuing. And you can see this chart that NOAA put out by the Global and also the Global Warming Policy Foundation. That looks like Josh's handwriting there at the bottom. All of these tremendous agreements that we've been told have happened. Do you see any impact at all that they've had on that rising CO2 line? I don't see any. In other words, the world is going to keep going on this carbon diet because that is the most accessible way for folks to be taken away from poverty in the world today. And that's going to continue no matter what we think or do. Next. So in 2019, this is what I told the group. The average American is smarter than you think. They recognize that when an elitist is exaggerating a story, the end result of which is to deny this average guy some aspect of life he or she wants and needs, while the elitist maintains a luxurious lifestyle. Now, this is my comment for today after the election here in the United States. By the way, things are going along fine as far as I can tell. No one's running out in the streets here demonstrating or anything. 2021, the average American is going to learn what a political party who wants to eliminate carbon usage is going to mean for their lives. However, if re-election is still a main driving force of the current party, perhaps this party will look for hard evidence to find excuses for not punishing the electorate with higher and higher energy prices. In other words, I kind of suspect that there's going to be people in the administration, no matter how loud they talk about climate alarm, who say, we want to be reelected in 4 years. And you really can't do that if you make a lot of people mad by taking money out of their pockets and giving them nothing in return. And that happens when you increase gasoline prices. You get the same gasoline, but less with more money. So therefore, you got nothing in return. You lost. Your wealth went down. And so they're going to have to worry about keeping the electorate at least somewhat happy. Okay, next. Now, you can imagine that some of these things I've said are very controversial over here, and I bet in Europe, they're just unheard of to hear many of these kind of things. And so when someone like me demonstrates that claims of climate campaigners are exaggerated or false, you're going to be isolated, denigrated, criticized from the climate establishment and major media. And now, in 2021, the elected federal government is going to be joining in on trying to criticize folks like me. And all I can come back with is facts. I think you saw slide after slide. What I was showing you was numbers, the real facts of the situation. Those don't seem to matter at this point, but I think somehow they are eventually. They're going to get into the system and they're going to make a difference, I hope. All right, next. I believe that's it. So thank you very much for having me, and I hope you enjoyed the talk today.